Okay, so this is my recording for homework for Broyden's method and Lagrange multipliers. Um, and the first question we have here is explain the advantages of the Broyden-Sherman-Morrison method over Newton's method. And that is mainly in computational power. Of the Broyden's method is significantly less than compared to that of the Newtonian method. And that is due to in Broyden's method, you only have to calculate the Jacobian and the Jacobian inverse one time, whereas in the Newtonian method, you have to calculate it every time through the loop. Um, the second advantage is that the Newtonian method is only one-dimensional, where Broyden's method can be expanded to n dimensions. And the third advantage of Broyden's method um, is that of, um, let's see, I said computation, um, dimensions, and the third advantage is round off. The Broyden's method contains less round off area than the Lagrange multipliers. And question 2 here, derive the Broyden update formula and its form when used in conjunction with Sherman-Morrison. So the actual, I think that should be Sherwood. Oh, it is. I've been calling it Sherwood this whole time, but it's Sherman. um, in conjunction with the Sherman-Morrison formula, I have another video up right now where I actually derive it by hand on OneNote. So question 2 can be found there. But we're also going to actually code the formula, code the Broyden's update formula in Google Collaboratory here. So for question 2 here, I've preloaded some Python libraries, which include JAX, JAX-NumPy, and then configuring JAX to enable 64 instead of 32 to increase our accuracy of our answer. And then we can get into creating this Broyden-Sherman Morrison method. And I have some notes here below to kind of help me out through this process. So the first thing we're going to do is define a function called BSM. And we are going to give it some inputs. So we're going to give it a function, we're going to give it an x, we're going to give it a Jacobian input where we're going to allow the user to specify a Jacobian or just say none if there is no input. We are going to give it a max iteration length of 500. We're going to give it an x max of JAX-NumPy infinity, and an x min of just the opposite. So JNP dot infinity. I actually forgot. I'm going to give it a tolerance too. So 1e to the negative 10th. I believe that is all the inputs we need for this function. So the first thing we want to do is to create the Jacobian for our function, or allow input for the function. So we're going to say that the Jacobian of our function is JAX dot Jacobian of our function, and also going to say if j is none, else j. That will give us what we need for user input Jacobian or to calculate it ourselves. And then we're going to evaluate the Jacobian at the given x input that we have. So jf of x. And then we are initially going to take Jacobian inverse, which is going to be JNP dot linear algebra dot inverse of our j. And then we're going to evaluate our function at x and call that f. And then we're going to start our for loop here. And our for loop is going to run for I in the range of our max iterations. And after that, we are going to utilize the Newtonian method, or I think it's the secant formula, to determine our dx here, which is going to be dx, so our Jacobian inverse matrix multiplied with our function. And then after that, we are going to use something here that we're calling alpha. And this alpha is going to be used to be multiplied by our dx to change, from what I understand, essentially the size of our dx to what we need it to be. So we need to come up with some constraints for alpha. So what we're going to say is J and P where, and we're going to give it a conditional statement of dx plus x. If that value is larger than our x max, then we want to rewrite this alpha max as x max minus x min divided by our dx. And if this condition, okay, then we're going to say 1. And then I also want to make sure we're grabbing the minimum value from this. So we're going to say JP min. And then we can copy and paste this, put it down here, and then specify an alpha minimum and change this conditional statement to a less than rather than a greater or. And then we're going to set our alpha value. So we want to take the minimum value between these 2 points. So we're going to say alpha max and alpha min. Yeah, and then now that we have that information, we can enter a while loop where we're going to be checking the size of our alpha value, because if it gets too large, I guess, or too small, our function here isn't going to converge properly. So while alpha is greater than 0.1, we will want to test our dx. We'll call this dx, and then we'll multiply it by that alpha value that we created above. And with that, we're going to make our new x, which is just our dx test. I have to call this something different. Dx test plus dx. And then value our new function at that new x that we just made. And then we want to check the distance it is from our previous function. So we need to say that the change, or the delta norm of JNP dot, well, I know I need FP, right? I need FP minus F. I need JNP dot linear algebra, the normal line of FP minus JNP dot linear algebra dot normal of F, our original function. And that will give us our D norm. Check D norm. And then what we want to do with that delta normal, and what I think that delta normal is doing is checking the distance between our original function and our function with this dx test as an input, and checking the distance from the origin from those 2 points. And then we're going to use an if statement to say, well, hey, if this D norm is greater than 0, we need to reduce our alpha because our step has been too big. So we want to reduce the alpha. And if it's not, then we can just break this. Okay. So we did this. We did the if statement. We reduced the alpha. Do we need to break the loop? And now, since we have reduced the size of our alpha, now we need to check to see if our alpha became too small. So we could say is 0.01. And if that is the case, we need to recalculate our Jacobian inverse. So we need to do JNP, that linear algebra inverse of our f of p of x. No, our not of f of p, or j of f, j of f of x. And even if that doesn't happen, we want to say that this continues, so we don't get out of this while loop. I think I can indent that like that. And then after that, we can update our variables, which consist of dx. So dx equals dx test, and our f is going to be our f. Let's do x equals xb, and f equals fb. And now we can check our convergence. So our f value, if that is converged to 0, or more accurately converged to below our specified tolerance. And if that is the case, we can exit out of this massive for loop in the function, update the values, and then get our outputs. So we could say if our function is less than our tolerance, and we need the absolute value of our function, we need all of 2. So jnp dot all. So if that happens, we want to calculate our Broyden, Sherman, Morrison function. So like in our video, we're going to have a u, and we're going to have a v, and then we're going to have our j inverse. So our u is going to be equal to the jnp dot expansion of dimensions of dx. No, the expanded dimensions, I want to say it's fp of 1, because I know this one is the expansion of the dimensions of dx1. Let's think about this really. So our v is the expansion of dx, and our u is the expansion of, I think it's just f. But I have a funny feeling about this. We'll continue on. And for this next part, this is actually, so this is calculating our J inverse. So this is Broyden and Sherman-Morrison's method derivation formula that we ended up with at the end of the video, that I actually have written down here in front of me. So we are going to say that our J inverse is going to be equal to our J inverse minus our J inverse, matrix multiplied by U, matrix multiplied by V, the transpose of V, matrix multiplied by J inverse, and then that whole thing divided by 1 plus transpose of V at J inverse at U. And that looks right to me. So this is actually our Jacobian inverse that we can calculate right here. And then after that, we can return our x and our f. So let's see if this runs. Name J and P is not defined. Okay. So it ran, and I'm actually going to pull up my other YouTube video that I had made. Let's go to my channel. Broyden's method derivation. We're going to go to the end here. If it loads, so my V is my delta X. This should be inverse. Where is it? U. Okay, we are going to go with this, and if I find a correction, I will mention it in the next part. But that looks right to me, and it ran, so that is good news.